Welcome to this conference session on doing statistics in Julia. I'm going to do an introductory talk on some of the big ideas. Then after that, you're going to get a bunch of specific talks on individual packages and problem areas. And then finally, we're going to go into a panel discussion with some of the cool people who are building things in this field. Okay, so let's get started. For me, the point of departure is, of course, R. Most people in the world of statistics tend to use R, and it's important for us to understand the strengths and weaknesses of the R world. The first thing to emphasize is that the strength of the R packages is simply remarkable. There's been thousands of people who have built extremely high quality packages in R, and there's a lot to be said for the intellectual capacity and the high software quality that has gone into the R package ecosystem. Now, from the viewpoint of a statistics user, there are many things about the syntax of R which come quite naturally, which come quite readily, particularly if you want to write 5-10 lines. It's a domain-specific language which is meticulously convenient for the people in the space of data science, for the people in the space of statistics. But that has come at a price. And some of the clean computer science principles of simplicity, consistency have been sacrificed in return for that ease of extremely nice 5-10 line script. And I think that these trade-offs have started showing, particularly now that we are doing really enormously complex things using R. So I think that there is modern computer science knowledge about what is a simple, clean, consistent programming language. And the trade-off that R achieved was an approachability and ease of access for the world of statistics in return for sacrificing some of the simplicity and consistency in the world of computer science. The next thing I want to point out is that the world of R programming has actually split into two somewhat different kinds of languages. There are the R programs written by old-timers like me, and then there is the Hadley-verse, the tidyverse, which is actually in many ways a very different language. Many times it seems like the two groups can barely read each other's code. So the R world is not as monolithic as it seems. Yes, of course, we can call each other's packages, but the ability to read the other person's program has diminished. I'm reminded of a joke about Perl that it's a write-only language. If you read your own code of a few years ago, you can't remember what the hell you were thinking. I know I have been in that place myself. And then we get to the problem of performance. In the last 10-15 years, data set sizes have simply exploded, and it is difficult to achieve high performance in R owing to some basic language design features that will not be readily eliminated without breaking compatibility with the language. So as a consequence, many researchers, many applications in the industry end up having to put in extra effort to overcome performance bottlenecks. There are broadly two approaches for doing this. Either we go more intensively into parallel computation, or we write something using RCPP, or we're linking into ancient Fortran codes, and that of course comes at a cost. So this is not free. The most important resource is not the CPU but the human mind, and the kind of effort many people are taking when confronted with these performance gaps is quite immense. My last idea in this is, of course, the familiar Julia argument about the two-language problem, particularly when there is a separation between a research stage and a deployment stage. It tends to often be the case that there is this step of studying the data and arriving at certain models, which is done in R, and then something is rewritten in C or Fortran or something else to be suitable to a real-world enterprise deployment, and that is painful and expensive. So I think that there's a two-language problem at two levels. Many R packages contain a great deal of C and Fortran, and then There is the deployment problem where enterprise IT applications tend to demand converting from an experimental or a research code in R into a production code into something else. So this is my sense of what is happening in the R landscape. Well, what are the possibilities with Julia and how does it shape our thinking for the field of statistics? My sense is that 10-15 years of progress in programming language design and software engineering has gone into Julia. I feel the syntax is clean, it is simple, it is elegant, it is consistent, particularly when you go beyond 10 lines, 50 lines to 500 lines. The differences are palpable and it's just a cleaner place to be building stuff. So I feel that the productivity of the programmer has gone up considerably thanks to the 10-15 years of progress and the simplicity of the language. I think Julia has been more careful about laying down the clean lines of modern programming language design. And then there are the performance gains. Everybody talks about how Julia is better. I want to tell a story about our own experience. You're going to see the talk about the survey package that my colleagues have built, and in the survey package we have seen that while we have enormous respect and admiration for the work that Thomas Lumley and others did in building the survey package, we find that our small Julia implementation of similar concepts for certain similar problems is giving performance gains like 100 times. 100 times is a lot, and it matters materially for the kind of projects that we are doing. And then exactly as I said a moment ago, if the person doing the applied statistics is investing time in going polylanguage or in doing a lot of work on parallel computation or in the separation between research and deployment, then some of these problems are eased, because in Julia we get to go with a one language and the same language can go all the way to a production deployment. So I think this is the case for Julia, that there is value added from the simplicity, the elegance, the consistency of a modern programming language and a supporting modern software engineering environment. In my opinion, the single place where the greatest translation of this promise of Julia into a living reality has taken place lies in Bayesian computation. In the world of Bayesian computation, we've gone through a long journey of bugs and then JAGs and then STAN, and in its own way we have had this two-language problem all through. So we are finding ourselves in the place of writing an R program inside which there is a STAN program, and that is its own kind of two-language problem. And there was a natural opportunity to make an all Julia workflow, because Julia has the modern computer science through which the Bayesian model can be written in pure Julia. And there could have been an approach of doing something more modest, but I really admire the people who have done Turing, who have done SOS, and they've played this at a higher level, they've played this at a bigger scale. And I feel it's not an exaggeration today to say that the best Bayesian statistics today in the whole world is done in Julia using Turing and SOS. And I think these are remarkable packages, and they have not done a mere reimplementation of STAN in Julia, but they've gone and thought this afresh using the modern computer science opportunities of Julia. And in my mind, this is a foretaste of where we can go in statistics in Julia. So we are not there. There are many pieces that need to be done, but in my mind, this is a demo of what a transformative gain can be obtained by rethinking statistics from the ground up using Julia. And that takes us to the perennial debate that when we build statistics for Julia, should we go for something that is more comprehensible for the install base that is coming from R? Okay, the bulk of the statistics of the world today is done in R, and so there are certain metaphors, there are certain interfaces that a lot of the user base is used to. Or should we go deep into a native Julia world of rethinking, of reimagining how these things can be done in the Julia world? And while of course there will be this perennial debate, in my opinion, I feel we should lay the foundations for a more profound gain, as the Turing and SOS people did. And so I feel that maybe there should be a compatibility layer, there should be code generators like the old F2C. There should be many crutches using which the install base can choose to move more readily. But fundamentally, a programming language that does not change the way you think about programming is not worth learning, as the old fortune goes. And here, I think our opportunity is to rethink this at a deeper level. So just like S was a revolution, just like R has been a revolution, I feel there is an opportunity here to think about statistics from the ground up in a new way, to bring new imagination to bear on this, and to build a new world which will actually be more expressive and come closer to our thinking as statisticians and make it easier and nicer for us to do statistical research. So we're not competing with anybody else in this game, we're competing with ourselves. Let's build something good. Now, in this, I think it's important to see that we don't need to leave the richness of our R packages behind. RCall is always there, and so we are never stranded. So in fact, whenever there is a particular specialized estimator, which is done very well by an R package, great, we should use it. So as an example, I have worked on an R package called FX regime, which estimates structural breaks in the exchange rate regime. It is perfectly accessible using RCall. So I feel that our way forward lies first in focusing on the 90% of the lines of a project, which are actually the everything else. Only 10% of the lines of a project are the actual statistical estimation. So our focus should be on the foundations, the data structures, the expressivity of the syntax, how we hook up to databases, how we connect into maps, the whole complexity of handling data, managing data, manipulating data, which actually eats up 90% of our time and effort and lines of code. These are the key choke points. Once these are done well, we are ready to move projects into Julia, and I hope the Julia statistics world already adds value when compared with some of the difficulties of our R world. And when it comes to the specialized estimator, we can always use RCall and drop into a beautiful R package and get our estimation done. So I feel our priority in building the Julia statistics ecosystem should be the everything else. It should be data structures, syntax, expressivity, and the surrounding infrastructure of databases and maps and parallel computation and so on. So here's an example from our life. We love data frames. What the pioneers in Julia and Bogomil have done in data frames is wonderful. And in the field of time series, we feel that there is remarkable capability in the R world, first in terms of the Zoo package and then in terms of the XTS package. They have built a whole set of metaphors and convenient expressions through which the finance, macro, and a whole array of other subjects are able to do time series analysis. So we built a Julia package that is called TSX, which borrows a lot of these metaphors and implements them using data frames. So it turns out that all the functions that we have built in TSX are just one or at most two lines of data frames. But the point is that they pick up the world of a time series programmer to a higher level, and so that we're not doing complex data frames manipulations, but we get the simplicity and the beauty of the Zoo and XTS syntax, so that basically you could be doing a complex time series oriented finance macro project in a Julia workflow. And then of course there will be times when you're doing a complex estimation of some likelihood function. At that time it may well make sense for a long time to drop into an R package to get your estimation done. But the viability of the main macrofinance workflow being done in Julia critically required this replacement for a Zoo XTS, and so we chose to build that in the TSX package. So what is our strategy going forward? Our strategy is that we are doing many interesting academic and other applied research projects in Julia. We are building applied statistics projects entirely in Julia. Every now and then we encounter an important bottleneck, and then we try to go and solve it. And we don't stop at half measures. We do the full software engineering, we build test cases, we write documentation, we fit it into the existing Julia package ecosystem. But our main driver is that We are researchers and we are doing applied statistics papers. With each of our papers, we are releasing the complete reproducible research code so that other people can see complete paper implementations being done in Julia, and that may help many other people think about this and hopefully build better stuff based on what we are doing. So far, we have a complete release of one paper. The title and the URL are on the screen, where there is a working paper and the complete Julia code, and by the way, an underlying Julia package, so that we've released everything and one complete implementation has been done in Julia. So this is going to be our strategy going forward, that one by one, we are engaged in moving our applied statistics workflow into Julia and solving many of the bottlenecks that come along the way. So to give you a flavor of who we are and what we have been doing, there are names of key persons on this slide, and I want to give a shout out and credit to many students who have been part of this work. It's great, the kind of team that has come together, the momentum that has built up around this development. And I just want to introduce some of the packages. CR Rao is our attempt at a single consistent API for a wide variety of statistical models. Nighttime Lights is the package for cleaning and bias correcting nighttime lights satellite imagery. Survey.jl is a package for working with complex survey data. TSX is a time series class that will be particularly useful for finance and macroeconomics, but also in any other area where there is regular or irregular time series data. And we've also done a bunch of smaller things. We've contributed improvements to the GLM package. We've built a LOS. We've built a Merton KMV model with a distance to default. So thank you for having been in this talk so far. Our URLs are on the screen. We'd love to have your interest and involvement in carrying this work forward. And as I said, in this conference session, we now deep dive into many of these things, and we're going to come out at the other end with a more strategic panel discussion about Julia and statistics and what works and what doesn't work and what we can do better. Thank you.
To this talk on the survey.jl package. In a nutshell, we are implementing a package for complex survey analysis in Julia. This is based on the R package survey by Thomas Lumley. We aim to provide a more efficient computing framework that is required for the growing sizes of datasets. Surveys have become a standard tool for empirical research in social sciences. They've also become an important tool in market research in the industry. Complex surveys involve sophisticated techniques such as stratification, clustering, unequal probability sampling, or sometimes a combination of them. One of the surveys that we study at XKDR Forum is the Consumer Pyramids Household Survey. The survey is executed since 2014 by the Center for Monitoring Indian Economy. There are 236,000 households in India that are surveyed thrice a year. Income from various sources, expenditure on certain goods and services, assets, health indicators, etc. are measured. Our common tasks include producing summary statistics, for instance, the median income for each state for each month, and exploring relationships between variables such as the ill health rate and income, as one of the working papers of XKDR has explored. A number of software tools are available to analyze survey data. The survey package in R is a widely used open source option. Professor Thomas Lumley of the R core team has developed the package. Version 1.0 of survey was released on 4th February 2003. This means it has experienced long years of stability and testing. Many resources are also available, including a book on how to analyze complex surveys in R and a research paper that highlights the technical details of the package. While the package excels in expressivity, it's not very performant. The package is completely written in R, while other packages use libraries written in C and C++. Advancements in the R ecosystem, such as using tables, haven't been incorporated in the package. This is probably because this will require changing the very foundation of the package. A Julia package can be an efficient alternative to the R package while matching it in terms of expressivity. Just a line-by-line translation of the code from R to Julia will result in a faster program. The performance can be further improved by exploiting the advancements made in Julia through various packages such as group by and combine in dataframes.jl. There have been attempts at implementing a package for survey analysis in Julia. I have mentioned 2 of these in the footnote. These haven't really materialized. However, it shows the interest on this topic in the community. As mentioned in the introduction, we are building a package in Julia for survey analysis based on the survey package in R. We will keep the API of the package as similar as possible to the R package, while the internal code will be completely different. It will be in a Julian way and exploit features such as group by and combine. We endeavor to achieve the following. We want to provide all the methods of the survey package in R, but in a more efficient way. We will provide a documentation that includes information on transitioning from R to Julia, and that will be illustrated through the examples that are provided in the survey package of R. The package will have numerical tests, including the cases that are there in the R package. And finally, we will have the cutting edge features of Julia, such as probabilistic programming. That's a lot for the future. Right now, we have implemented only a very small set of functions: mean, quantile, total, and generalized linear models. And a lot of stuff can actually be done just on the basis of these. As an organization, our primary objective is to do research. We will use this package to do research, and that ensures seriousness about the quality of the package and the correctness of the results obtained through it. If we obtain a result through it and that gets published in a paper, we will take full responsibility for that. At the same time, we feel that making it open source is necessary because it brings transparency. If there is any problem in our research, people will be able to find it out and point it to us. We will be happy with the criticism that people give us, and perhaps the help that they give us to improve the package, which will improve our research. Now I come to the second part of this talk. I will show you the R and Julia code side by side. I'll compare them in terms of expressivity, accuracy, and also perform benchmarks. So on the left, you see a Julia REPL, and on the right, you see an R session. So now we will load the libraries. In R, you would do library survey, and in Julia, you would say using survey, but with a capital S. We load the sample datasets that are provided with the package. Data API loads the API dataset. This includes 5 datasets, and we will use the API stat dataset. In Julia, it's the same syntax: data parentheses API. And again, you have all the API datasets, and we will use API stat dataset for this tutorial. To begin, we create something called a survey design. This contains information about the dataset and how or what kind of sampling was used to create it. For example, in this case, we say ID equal to tilde 1, meaning that it's a stratified sample. Given a column name instead of 1, then it would be the clusters. Then it also contains information about which column contains the weights. It can also be probabilities. You can mention either of them, and you can also provide a vector for these instead of a column. You can see that the syntax in R and Julia is very similar. So instead of telling the column name using a tilde, we are telling it using a colon. So now we'll demonstrate the survey by function. This can be used to compute mean, quantiles, and total. In this example, we will compute the average of the API 00 score for each county. You see the similarity in the R and the Julia syntax. Again, instead of a tilde, we have a colon. We have not yet made these into keyword arguments. We are working on that. But you see that overall the syntax is quite similar. There are some differences in results. You can see it in the case of Orange County. The standard error answers are not exactly matching. This is because R performs a series of corrections on top of a regular standard error. We have implemented some of these corrections, but not all of them. And perhaps this could be one of the reasons for the speed, but I don't think that it's the entire story. However, standard errors are essential to survey analysis because using the techniques such as clustering and stratification, you aim to reduce this standard error. Now we'll come to the final function of our current package. We'll use the GLM function to find the relationship between API scores and number of meals. You can see the coefficients are nearly the same, both the intercept and the slope. We do store the other parameters that are there other than just the intercept, such as the AIC score. The AIC score, as you see, is quite different between R and Julia. This is not a GLM that we have built. We are just using the glm.jl package that exists in Julia. And we are exploring why this number is different. Now I'll come to the benchmarks to show the difference between performance in R and Julia. I've used the micro benchmark library in R and the benchmark tools library in Julia. I will use the same functions that I've used earlier, so the same survey by call in both R and Julia. I believe the median time is about 350 times less in Julia. But now I will increase the complexity a bit. Instead of just grouping by the county name, I will group by two variables. This is county name and meals. It doesn't make much sense, but just to show the performance, I will do that. So Julia seems to be a lot faster, and it seems even faster when you're grouping by multiple variables. This is probably to do with the group by and combine feature. Finally, I'm going to show you the benchmark for the survey GLM feature. I will use the same call that I had used earlier in the example. So the SVY GLM feature for this example is about 30 times faster in Julia compared to R. I thank you for watching this talk. The survey package is not ready right now, so I'm not going to advise you to try it out. We acknowledge the support from MIT Julia Labs for this project. We thank Carlos Parada and Jose Santiago for their guidance on this project through Google Summer of Code. And finally, we thank Ajay Shah and Mausam Datta for their very valuable inputs.
Good afternoon and good evening. And my name is Vijay Evaturi. I am the co-founder at Pumas AI, a company that was formed about 3 years ago using Julia language as a core ecosystem. And today I'm going to be talking to you as an applied scientist. I'm not a developer, and I've extensively used multiple languages, and I am a statistician. But there are different kinds of statistician, and I would love the tools that I use to be my slave and not me being a slave to the tools. So the topic of my presentation today is about empowering the statistician. And when we talk about the statistician, there are many different kinds. I am the self-trained statistician. I'm not a professional statistician. And nowadays, you have the hobby statisticians, especially in the era of COVID, where data was available and everybody wanted to analyze. But if you want to think about it, pretty much everyone has some trait of a statistician within us. We make decisions on a day-to-day basis, and we apply those decisions to provide solutions, whether it is in the home front or in the work front. But focusing a little bit more on the scientific aspects, scientists, let's start by understanding and playing a small game. Could I ask you to identify the statistician in this? On the left is Jack, and on the right is Joe. Jack is a trained clinical pharmacologist, somebody like me, who had the opportunity to learn and learn and train more in statistics and use those statistics in his day-to-day work. Joe, on the other hand, has a strong technology background and was trained in professional statistics and applied mathematics. And for Joe to make a career, he has to work with other fields like people like me, so that there is the science that is applied and the solutions are provided using statistics. At the end of the day, all of us wear multiple hats. It doesn't matter what domain we come from, we have to work with other domains to provide solutions that are meaningful for our clients. And if you bring all of this together, the idea is that we all talk about collaboration. Different domains need to work together to bring collaboration and make successful solutions and successful products. Let's take an example. I'm sure all of you know about Uber, and the way Uber became a billion-dollar company is by using the APIs that were generated by each of these individual products. There was an ecosystem that existed, and this ecosystem provided the absolutely wonderful APIs that allowed Uber to compose them together, and boom, it became a billion-dollar industry, right? And on the other hand, Uber gave it back. Uber released its own APIs, and you see now Uber integrated into, let's say you want to book a table at a restaurant, you just open for example, the Open Table app, or you can, even if you open Google Maps, you see the pop-up for Uber. You want to go catch flight United or Delta, you open the app and you have Uber integrated there. So Uber has released its own APIs which allow other businesses to succeed. Now, why am I talking about this? The fundamental core here is that there is no success without an ecosystem, and there is no ecosystem without composability. And Julia language is brilliant in providing the composable features of its language. The packages, they all just know just how to talk to each other. But let's sort of bring this back into a more understanding. Why are we even talking about this? Now imagine Jack and Joe wearing those different hats. They have different expertise. And imagine in the same model of contributing to a particular product, the product here is a statistician, right? And we're talking about each statistician wearing multiple different hats. And if each of these hats are able to provide an ecosystem that allows that particular individual to analyze data, then it will become easy for that statistician. So our goal is to make it really easy for the statistician in the making. We are all statisticians. And I know the professionally trained statisticians are going to be really angry, but the truth of the matter is everybody is analyzing data. It is true that we may be making a lot of mistakes. It's true that the applied self-trained amateur hobby statisticians may not be doing it the correct way. But I think it's the job of the ecosystem to provide the necessary tools and education to be able to train anyone to do the science better. If you look at the first principles of any domain, and I'm looking at this as a unilateral principle, every domain has its first principles. And if you want growth and propagation, the first principles need to be taught well, and you need to provide the tools. Now think of this from a multidimensional approach. You're now talking about first principles across multiple domains that need to integrate well, and you need to provide the tools and education to allow the growth and development of the critical mass. So to empower the statistician, which is the title of the talk, we really need to invest. And I think Julia language, has to really invest a lot more into education and tools. We already have fantastic tools, but those tools should allow easy usage. And they are easy to use, but bring it to the next level, bring it to the masses. The problem right now is that there are a lot of hurdles. It's pretty much like an entrapment, right? If Julia language is a first language that I'm learning, then it's not going to be so convoluted. But we're trying to move an ecosystem of users from other languages. And when they come into this world of Julia language from, for example, R, they're obvious to face some hurdles. And these hurdles are natural, and we need to do our best to sort of cut those hurdles out. From a natural perspective, we expect our analytical tools to be organized. I'm a clinical pharmacologist. Maybe somebody is an epidemiologist. They will use those tools. Maybe somebody else is in another domain. They will use this particular tray. If you look at how these trays are organized, they're easily discoverable. They're clearly marked with colors. They're numbered, and they're easy to use, perhaps. They've been set up for different kinds of use cases. This is the expectation that it doesn't matter which domain you come from, whether I'm coming from clinical pharmacology or whether I'm coming from time series analysis or whether I'm coming from fluid dynamics, it doesn't matter. Different kinds of domains need to have the tools to perform that analytics. The core tools are important, but we need the tools on the top that will make it organized, discoverable, and easy to analyze. But the challenge right now has been, so far, across the other ecosystems, that these tools have been disorganized and not accessible. Maybe this is too bold a statement to make, but the fact of the matter is we need more organization, education, and tooling to allow the growth of the critical mass. Julia provides the opportunity for the growth. It's composable. You can teach Julia as you learn the science. You can teach Julia as you learn the math. And the problem right now is that especially with the statistics ecosystem, it's a relatively small user base. And the Julia way of programming has an on-ramp. So people coming from other languages strive to do the Julia way of programming. And the beautiful part about this community is that, scientists are very helpful, especially if you go on a discourse. They're very, very helpful and help you get along. We need more of this. And obviously the challenge about time to first everything. I know it's considerable amounts of improvement that has happened over the way, especially with the ability to have the binary builders and system images that have really helped even us at a company like Pumas AI. So there are pros, and we need to build on these pros. And the easiest way to build is through providing world-class educational material. We need to document the packages and train the domain user and not just the next developer who's going to use your package. Yes, you should provide your APIs for other package users to use it, but we should focus on the end user. And the end user of your particular package can be from anywhere. The classic counter to this is that, well, they're developing the packages for free. We need resources to be able to do this. Absolutely, this is a challenge, and companies like Pumas AI and others are helping and we are ready to help in any way that's possible. The other thing which I really think is important is to allow anyone to do, and when I say anyone, not just a professional statistician, but the self-trained, the amateur, the hobby statistician, to try things out and go from trying things out to writing about it, to publishing about it, to blog about it. We need more presence in the community. And I think the tools to facilitate going from doing a simple analysis to publishing it online should be, the friction should be close to zero. Imagine me having to now learn how to spin up a server and do an HTML blog. I mean, it's beyond 90% of the population. So we need to make it easier. And lastly, we should incentivize more programs to teach Julia as a first language and statistics tool. I think this will happen over time. This is already happening at the university that I'm involved in, and I am pretty sure there are a lot more universities that are coming up. There are excellent books that are being released, and I think we are on the right path. We are at a very opportune time, and we need to empower every statistician and take it to the next level. We have the opportunity to innovate, completely change the mindset and say, let's build the next generation, and the crowd will follow us. The current generation will also follow us. So in closing remarks, I would say that we need to strive to empower every statistician, whether they're a completely professional statistician or self-trained like I am. I think at that, if we can achieve that, that is what will allow the growth of the Julia statistics ecosystem. Thank you, and I hope to hear back from all of you. Bye.
Very much for giving me the opportunity to speak in JuliaCon. In this talk, I'm going to talk about CRAW, a new package, a single API for diverse statistical models. Many statistical models can be trained in Julia, and diversity of the model ecosystem is steadily improving. Drawing inspiration from Zelig package from the R world, the CRAW package gives a simple and consistent API to the end user. The end user faces the fixed cost of getting a hang of this once, and after that a wide array of models and associated capabilities become available with a consistent syntax under the umbrella of CRAW. We hope others developing statistical models will build within this framework. Let us consider a simple linear regression. So we are considering this empty cars dataset where MPG is miles per gallon, HP is the horsepower of a car, and WT is the weight of the car, and I want to predict miles per gallon as a function of horsepower and weight, plus some error terms where error follows normal 0 sigma square. A likelihood model will follow effectively multivariate normal with alpha naught plus x beta, where alpha here is essentially my beta naught, and x beta will consist of beta 1 and beta 2, and x will consist of HP and weight. So here in this CRAW we have this simple macro at fit model, which basically models the MPG follow HP plus weight, and then we have taken this data set, empty cars data set, from our data set. So DF contains the empty cars data set. So you provide the data set and then you just tell what model class you want to fit. Let's say linear regression. So you just say that, and then if you run this, it will give you the linear regression estimates. Yeah. So the intercept coefficient estimated, standard error, t-value, p-value, and the 95% confidence intervals, you can get it from here. You can get the say BIC of the model. If you want, you can find AIC of the model. You can find say R square of the model. So R squared is 82.67%. So all standard things are available under CRAW package. Now we did a check of the performance gain, and in R we micro benchmarked exactly same model MPG with HP and weight with this exactly same data set, and it took about 380 microseconds and on an average. And when we did the the same thing we checked with the Julia, it took about 160 microseconds. And then what we did, we also compared it with the Python. In Python there are two packages. One is stat models, which calls the OLS function, and the more popular one is sklearn, which calls the fit function. And very interestingly, we found that stat models is very inefficient. We don't know exactly why it is so, but sklearn is taking about 560 microseconds, whereas R is taking about the LM, which is most popular for fitting a linear regression with stats, is taking about 280 microseconds, and our CRO's fit model is taking about 160 microseconds. So performance is only one aspect of Julia. As a statistician, I feel strongest feature of Julia is you can write your own code the way you write your mathematical equations, and that becomes very useful when we do Bayesian linear regressions. So if we want to model the Bayesian linear regression with, say, Rich prior, which is also known as conjugate Gaussian prior or equivalent to L2 norm penalty, then all you have to do, just this is your prior. As if it is on my board, I have to write typically that, okay, these are my hyper prior parameters, and V is follow inverse gamma H, sigma follow inverse gamma H0 P0, alpha follow normal distribution with 0V sigma, and beta follow normal distribution 0V, and Y follow likelihood multivariate normal with alpha plus x beta comma sigma. Now I write these equations on the board. The advantage is in Julia this code actually works and run. So what we have done in here, that you don't have to even you can do this in Turing. You can literally in the Turing.jl package, you can write the way you write in the board, you can write it in the Julia, and that runs, and that implement the Hamiltonian Monte Carlo or quantum Monte Carlo, and then it gives you the results. For us, what we have done, we have used Turing as under the CRO. So basically CRO is calling Turing to implement the Bayesian linear regression. So if you look at everything else is exactly same. So the model is MPG going to fit HP plus weight with the data frame as the where the data is stored, and linear regression. So if you don't put this is if you just give this much, then what happens is it fits a simple linear regression with OLS method. You see it is fitting a simple linear regression with OLS method. But now if you instead of just add prior reach, so immediately CRO would know that, okay, you want to fit Bayesian linear regression and with reach prior, so it will, instead of calling OLS, it will call the Hamiltonian Monte Carlo using Turing, and it will run the model in that way. It took about 0.02 seconds, and now if we run so what we are seeing here is the parameter statistics. Though it has by default it has simulated 10,000 samples, Markov chain Monte Carlo samples. These are the posterior mean and the posterior standard deviation, and R hat for all the parameters is very close to 1. So that means the MCMC has been converged, and this is the kind of 95% credible interval for the coefficients and the parameters. And so if you plot the chains, then so you can see that mostly this sigma has converged. I mean, it's nicely, the mixing is very good, and so this is pretty much, and all the like beta 1, beta 2 and the alphas, everything is there pretty much. All right, so then what you can do, you can fit also the lasso penalty on the L1, or sometimes known as the Laplace prior. So Bayesian linear regression with the Laplace prior. So everything will be the same, like I'm taking inverse gamma on the scale parameters, and on the coefficient, instead of normal, I'm taking Laplace prior, and rest of the things are pretty much same. So now the changes that you will have, instead of reach prior, you just mention here Laplace prior, and that's it pretty much. Rest of the things will just follow the same way. Plot the Bayesian chain. So it's just like almost all the chains have converged very nicely. If you go back, you can see that it's actually implements the Turing package. If you can see that actually it is calling Turing package, and it is actually HMC, Hamiltonian Monte Carlo methods there. They're implementing Hamiltonian Monte Carlo. So the convergence I have seen for even quite complicated model, it's very stable, and Turing is doing fantastic work in terms of fitting Bayesian models, and we are taking full advantage of Turing in CRO. So you can ask me that if I have Turing, why I should call CRO. So CRO is for the people who are not well trained in, say, Bayesian computation, but they are like practitioners, scientists, applied economists, and biostatistician who are not very well versed with the Bayesian computation, who does not want to write their own Bayesian MCMC or HMC. So they want, for them, some standard models are being given. We are going to give them a standard Bayesian models as a part of CRO. So they just call this fit model, give the model whatever model they want to fit, whatever data set what they have, whatever model class and whatever prior they want to use, just mention that, and rest of the things will follow on its way. So that is what we are thinking in terms of implementing CRO. But if you have a very specialized model in your mind and you are okay to write down your code, and in Turing, and if you have a very customized model that you want to build, then I think you cannot have better than Turing, because I have spent a lot of time in RStan, and it's oftentimes a nightmare, because effectively it is a 3-language problem, because first you have to have R on your place, then you have to have C on your place, and Stan, and these 3 languages needs to be have the same version. It sometimes if you have a Windows, you can have a very different kind of problems. If you have a Linux, you can have a very different kind of problems, and and Mac will have a different kinds of problems. So you can face very, very different. When it comes to implementation, RStan works fantastic, but in terms of speed and implementation, but in terms of generic implementation, Stan can be a bit of a nightmare. Compared to that, my experience is Turing is far more seamless, just works like this without any hiccups. So I am very recent convert, I would say, from R stand to Julia Turing, and we are taking the full advantage of Julia Turing in the CRO. So this is what we are seeing there. Now, what are the list of the models that CRO can solve? As of now, it can solve linear regression, logistic regression, Poisson regression, and negative binomial regression. For each of these four models, we implement the following methods: the likelihood methods, or the often known as frequentist method. Among the Bayesian methods, you can implement Rich prior or Gaussian prior equivalent to L2 penalty, Laplace prior or Lasso or L1 penalty, Cauchy prior, T-distributed prior, and uniformly distributed prior. So these are the things as a part of the current capability of CRO. For example, if you want to fit, say, logistic regression with the logic link. So from the Zelig dataset, we are taking the turnout dataset, and we're just calling fit model. Here is the model, vote as a function of age, race, income, and education. Dataset name is turnout. Here you can see this is the turnout, and we are calling logistic regression with logic link. So if you just run that, and then if you just run that, this here is your fit. So this is what you are seeing is just frequentist fit of logistic regression. Now, if you want to play around with the link function, instead of logit link, you can try probit link. So all you have to do, probit, you just write it here, probit, and run it, you get your probit link implementation. If you want Cauchy, you just change it, you get the Cauchy. If you want C-log, and you get the C-log implementation. Now, if you want to fit the logistic regression with a logic link, so you just mention it here, the same model, but with Rich prior. All you have to do, just mention Rich prior here. Previously, in the previous implementation, there was no prior here. No prior, then it will implement likelihood method. But if you have a prior, it will implement MCMC method immediately. It will identify that problem, and that, okay, you are looking to fit a prior, means you are going into the Bayesian version, and it will fit a prior. It might take few seconds, but you can see that first of all I will check for the R hat, and you can see that all R hat are very close to 1, so that means all the coefficients has converged, and you can see the estimates. These are the estimates, and these are the standard deviation of the posterior standard deviation. And if you plot this thing, you can see that all the chain has converged nicely, mixing is very nice. So currently, what are the things that are under development for CRO? So right now we are implementing linear discriminant analysis, survival analysis, bootstrap inference, hierarchical Bayesian models, and Gaussian process regression. It is not possible for us to implement this without the great help from Professor Alan Edelman and Viral Shah, and of course a great team is there, Siddhant Chaudhary, Mausam, Ayush, Ajay, and Susan. All of them have contributed to the greatly from designing the package, from computing from a very basic things, cleaning up, tasting, everything was done as a teamwork. And thank you all. Thank you very much.
Welcome to the Julia conference. Proc GenMod in SAS and RGLM are two most popular modules in statistics, and both are in place since last 2 decades. GLM in Julia is comparatively new. We did some comparative studies in the beginning of the year 2022. Let us present some of them one by one. Two main aspects of a generalized linear model are distribution family and link functions. Let's see where Julia GLM is positioned right now. Except geometric distribution, almost all one-parameter exponential distributions are available in Julia. But geometric distribution is the special case of negative binomial distribution. So one can do modeling with geometric distribution indirectly. But R and SAS both have bigger ecosystem than generalized linear model. There are many extensions of R's GLM, especially zero-inflated models, and 3D, are not available in Julia, at least a stable version. The list of link functions is quite impressive. The one and only missing link function is power link. The power function defines the class of transforms that use a power function or logarithmic function as it is shown here. Many existing link functions are a special case of power link. For example, it is identity link when lambda is 1. It is square root link when lambda is zero point 0.5. It is log link when lambda is 0. It is inverse link when lambda is minus 1. It is inverse square link when lambda is minus 2. The benefit of having power link is we can find optimal lambda value using some optimization methods, especially some heuristic methods. The example shows here a way to find optimal value based on BIC. One can use any other method like AIC, AICC, log likelihood, etc. to get the same. Now let us see how Julia GLM performs with some extreme data. This is a dataset or table I used to torture the numerical routines I have written. I have inherited the dataset from Professor L. Wilkinson, the author of Grammar of Graphics book. If we look at the data carefully, we can observe the relation between variable x and tiny. Variable x can be expressed as 1e to l times of tiny. If we want to perform a linear regression with intercept where x is a dependent variable and tiny is the independent variable, like x equal to a plus b times tiny, then we should have 0 as the estimate of a and 1e12 as the estimate of b. Unfortunately, Julia LM produces something else, whereas R produces correct one. Now let us extract model matrix M and response vector Y and calculate M prime M inverse times M prime Y. These matrix operations give estimates of linear model. These estimates are correct. Julia GLM uses Cholesky decomposition, which is very fast compared to QR decomposition or SVD decomposition, but less accurate, especially for ill-conditioned data. Okay, for huge variable, both R and Julia GLM calculate same and estimate correctly. NIST, National Institute of Standards and Technology, archived a set of 11 datasets with corresponding linear model and certified estimates. NIST claimed that certified values are accurate till last decimal places. We have tested both R and Julia LM functions with these datasets. Now let us take one from the list, which is no int 1, a dataset where corresponding model does not have any intercept term. We can see both R and Julia produce same estimates, and the estimates are matched with the certified value. In case of R squared, R matches with certified value, but Julia unfortunately produces a negative value. This has been corrected in the latest release V1 version 1.8. Now let us compare the performance. To have an idea about the performance of Julia GLM, we have performed a logistic regression with 50 independent variables and approximately 3.5 million rows. We have tested the performance in Linux machine with these configurations. Based on 20 evaluations, the median time for Julia is approximately 5 times faster than the median time for R. This is not only because of Cholesky decomposition, but Julia GLM utilizes maximum possible resources. As we all know, the computational backbone of Julia is very strong. The following are our contributions to Julia GLM. We have added power link function and geometric distribution. We have corrected some functionalities in GLM for models with no intercept so that it produces correct metric like R square. We have also tried to improve readability of GLM documentation. Right now, multicollinearity is handled only in LM function using the keyword argument drop collinear. Still, GLM function throws an error if there is multicollinearity in the dataset. We have raised a pull request to incorporate drop collinear feature in GLM function like LM function. We are grateful to the Julia Stat community, especially to Mr. Milan, for making these PRs successes.
Hello, a very good evening to everyone. My name is Chirag Anand and I'm going to talk about TSX, which is a new package to deal with time series data in Julia. So, why another package? When we moved from the R world to using Julia to solve our problems in finance, we encountered a few issues. We found out that the syntax to use time series operations wasn't very convenient or natural. We have been users of Zoo and XGS in R for many years and have used it to solve various kinds of complex problems, and we believe that is the correct idiom to solve time series specific problems. Those interfaces just feel natural. Then we saw that a lot of these time series packages have custom data structures, and hence a lot of code has been written to solve the same problem, which is not really consistent across all the packages because the data structures are different, and hence it is as difficult to maintain. If we look at the entire ecosystem, it's not very efficient to have different packages solving the same problem, and they need a lot of coding effort to maintain. Then we found it challenging to deal with heterogeneous data in the same table. These days, one data set contains everything from float to integers to categorical variables. It is not that one table contains only one type of data. So these were the challenges which we faced, and this is the reason why we thought of starting a new package. So what were the design goals of TSX? Well, so first and foremost, we wanted to utilize an existing widely used and well-tested package to promote code reuse and avoid duplication of coding effort. This also results in easier maintenance. Then we wanted to handle heterogeneous types in time series data in one table more easily. Of course, as I mentioned earlier, we wanted the package to have a more convenient and intuitive syntax to deal with time series operations. Then another design goal of TSX was to enable and allow custom index types, multiple types of index, which is that the package should allow integer indexes, it should allow date indexes, it should allow date and time indexes, and so forth. So this is something which did not we did not find. And a shout out to Ahim Zailis's Zoo package and the XGS package in R, because we learned a lot from these packages and we have used those learnings to build TSX. So after looking at our design goals and using all the packages, doing a lot of research and experimentations with the existing time series packages in Julia, we settled down at this data structure. As you can see, the primary data structure, it's called TS, and there is only one property of this structure, it's core data, which is nothing but a data frame. We settled on using data frame at the core of TSX because data frames.jl is one of the most widely used mature packages out there. It's well tested and provides all the functionality which is probably needed for doing all kinds of time series operations. The only thing is that the data frames interfaces are not very convenient to do time series operations. So with TSX, what we aim to do and what we have done is to build wrappers on top of data frames methods. These wrappers are easy to use for doing time series operations. Using dataframes.jl has other set of advantages. As I mentioned, it's well tested. It's used by a lot of people, so bugs are reported more often and there is a big community around it, and these bugs also get fixed quickly. Then, because a lot of functionality is already built and the community is already maintaining it, it will be easier to maintain TSX because of this reason. Most of the methods which are written in TSX are just a few lines of code, just because data frames already provides that functionality. After deciding to use data frame at the core of TS struct, we decided to keep the index of the data as the first column of the data frame itself. So during construction of the TS object, the data is sorted using the index column. How to use this is what I will be covering in the later slides. So the reason why the index was kept as a column inside the data frame was because it is much more convenient to use data frame data transformation operations if the index is part of the data frame as another column. As I mentioned, we've written wrapper functions over data frame transformation methods, and which provide a convenient syntax for time series operations. All the functionality provided by dataframes.jl comes for free, including the performance and robustness. Then another feature of TSX is that it provides easy conversion between TS objects and data frame, which enables use of functionality provided by many different packages, because data frames is really used by a lot of packages. And any package which supports operations on a data frame will support operations on a TS object also. Then the other advantages, another advantage of using data frame is that handling of missing data comes by default because data frame already handles it. So the basic constructor of a TS object is just uses a data frame as the first argument. The first column of the data frame is assumed to be the index of the data. If it is different, then it can be provided as the second argument. So the second easiest way to construct a TS object is to use an array. Here we have created a date range from 1st of January 2017 to 10th of January 2017. There are 10 dates, and we are generating some 10 random numbers. The first argument is the array of random numbers, and the second argument is the date range, and you can create a TS object using this. Then this is the most widely used use case of reading CSV files. Now, as you will see, this is quite easy. It's quite easy to use to read in a CSV file and create a TS object out of it. Again, this functionality comes for free because there is already a sink for a data frame in the CSV package, and because TS structure only has data frame as its only property, so it's easy to convert from data frame to a TS object. So these are some of the methods which are supported currently on TS objects. Because this is a new package, there is very basic functionality which is available, but it works. So we have the apply function, which can be used to apply a function on your data, and which can be grouped over a time period. Then we have a function to apply another function over rolling window of a specified size. Then we have a function to join or column bind two different TS objects into a single object using index as the key. Then we have vcat or row bind operation, which can combine two TS objects row wise while matching column names. Then we have diff, which can be used to compute discrete differences over successive row elements. We have log to compute logarithm, lag and lead to compute lagging and leading series. We have a basic plot function which plots the time series table with index on the x-axis. Now we look at three problems from the finance world. We use daily stock returns data and perform some operations on it. We perform the exchange rate regression, and then we handle intraday data all using the TSX package. So the first step for problem number 1 is that we download data from Yahoo Finance using the market data package. Here we are downloading data for two symbols. One is a stock called ITC, and other is the Nifty index. We download this data and then convert it into data frame and then to TS objects. Market data returns a time array object, so which cannot be directly converted into a TS object as of yet. In the future, we should have that functionality. As you can see, the data set, the first column is the index, which has been automatically converted by TS, and then we have the values open, high, low, close, adjusted close, and the volume. The second step to this is to join closing prices of both the series. We are interested in adjusted close, and what we do is to take the intersection of the index of both the series and create one data set, one table out of this. Because the join operation created different names, we have to rename the columns to their original symbol names so that we can use them conveniently later on. So this is how the data now looks like. So we have two columns, ITC and Nifty, and the index contains all the dates for which the dates for which data was present in both the symbols, both the securities. The next step is to fill in missing values which may have existed in the original data set or may have been introduced after doing the cbind or the join operation. We use impute.locf from the impute.jl package to perform this operation. Since impute.locf doesn't directly work on TS objects yet, we are using the core data property of the TS object, which is the data frame, which is the underlying data frame. We take the underlying data frame, we pass it into, pipe it into impute.locf, which fills in the missing values, and then we convert it back into a TS object. As you can see the output of the described function, there are no missing values left. The next step is to convert the series into weekly frequency. For this, we are using the apply operation. This is pretty easy. The first argument is the TS object itself. The second argument is the period, which is a subtype of the dates.period structure or the dates.period type. The third argument is the function to apply to each group belonging to the same frequency. Here we are using last, so this apply will pick up the last observation from each week. The fourth argument is also a function which is for the indexing operation, which specifies the index value to use for the single value which has been taken from the group. As you can see in the output, the last value has been taken and the last index value has also been taken from each group belonging to the same week. So you can see the index, they are a week apart. The next step is to compute log returns, which we do easily again by using the log function and then doing a diff over it. And as you can see, the log returns have been computed for both the series while maintaining the index. Now we want to run a simple market model regression, wherein there's the first step, which we create a formula where we have the response variable as the stock ITC and we have the Nifty index as the predictor. So we create the formula and then we use the lm function from glm.jl package to run this regression. Again, the lm function works on a table format which is provided by data frame. So we can directly use the core data property of the TS object to run this regression easily. We put in the formula as the first argument and TS returns core data as the second argument, and these are the results of the regression with the coefficients, the standard error, and the 95% confidence bands. The next problem is the exchange rate regression. So here some of the steps are similar to what we have done earlier. For example, we will be downloading the daily data for the currency pairs. We will be converting the series into weekly closed data and fill in the missing values. Then we will create log returns and do a simple regression. The next step will be to do a rolling window regression with a window width of 100 weeks. And then we extract the moving window values of a currency pair's coefficient and compute the residual standard deviation. Then we plot the results of this rolling window estimates. Again, we use a market data function to download data from Yahoo Finance. We download 5 currency pairs. Then in the second output you can see the structure of one of these currency pairs. There is an index. The data starts from 2003 till 2022. Second step is to join this data, join all the currency pairs into one object, and we again use the adjusted closing prices. Here we are using the inner join function from the data frames package because TSX currently, the join operation in TSX currently doesn't support joining more than 2 TS objects. But the join operation of TSX uses this data frame function only. So this is the output when we combine all the 5 currency pairs into one. Again, we have data from 2003 till 22, and we have 5 columns. We rename these columns because after the join operation they have been changed. Then we convert this object of adjusted closing prices into weekly data after filling in the missing values. This is again a simple operation of using code data, using the data frame of the TS object and putting it into impute.locf and then converting it back into TS object. Once we have the missing values filled, we use apply again, like we did it in the previous problem, to convert this into weekly data and take the last observation. This step is to compute the log returns. Again, similar. We do a diff log of the weekly closing prices and we rename it, and this is how the final data set looks like. Now we compute rolling means with a window size of 200. We use the function roll apply. We use the statistics.mean function, apply it to the returns object and the INR CHF column, and the last argument is the window size, and this is the result of this operation. The next step is to apply rolling regression with a window size of 200, wherein what we need to do is to create a function because we want to use all the currency pairs as the predictors here. So we want to write this function. So the formula contains INR CHF as the response variable and all remaining 4. Now what we wanted to do really was to do a roll apply of this function on this object and just provide the window size. But change rolling functions.jl, which may or may not be possible, or develop something from scratch or use some other package. But this feature is on TSX roadmap. This is an important feature to have in a time series package because this is a very common finance problem. So we will eventually have this in the package. Now we come to our third problem of handling intraday data. Here we use two CSV files to read an intraday data, which is at a millisecond level. This is simulated data because we did not have access to real intraday data. This is the structure. There is the index, we have the price as the second column, and then we have the quantity. We have converted both these data sets into TS objects. Now the first step is to convert them into 15-second observations. For this we again use the apply function, but in the second argument we supply the second, which is a type defined in the dates package, but we supply it with the 15 as the parameter, which means every 15 seconds. Like 15 seconds is what second parenthesis 15 means. In apply, it means that the data will be grouped for 15 seconds after every 15 seconds. Each group will contain 15 seconds worth of observations, all the observations which have happened in those 15 seconds. The third argument is the function which we provide to pick the observations in each group. Here again we are providing last. It will pick the last observation of the 15 second of each 15-second group. The last argument is index at, which decides the value to be used in the index for the value which has been picked up from the group. Here what we are doing is that we are taking the last second of the observation, because our data is at millisecond level, but now we are converting it into second level, so the index values should be at the second level. And the last argument, this is the function, this is what it does. I'm sure there are better ways to do it, and we will work on this to make it much more convenient, and this is slightly more complicated expression to achieve this. Now we create a single TS object using the join operation. We take the prices of both the securities and combine them together. Here the third argument to join is join all, which means take the union of the indexes in both the securities. Earlier we have seen join both, which is the intersection of the indexes. This is how the data set now looks like after doing the join. And we rename the columns price underscore last and price underscore last underscore 1 to ITC and Nifty, which are the symbol names. Now we compute the returns. Again, the same formula of doing a diff on the log of the TS. This gives us the log returns. Now we plot the squared returns. We use the plots package. On the x-axis, we have converted the date time into time, and on the y-axis, we have the squared returns of Nifty. This is the regression bar plot. Here we have first removed all the rows which contain missings using impute.filter. Again, impute.filter doesn't yet work on TS object, but it works on data frames. So we are using returns.coData, the coData property, and we have specified dimension as the rows. The output of impute.filter has been converted into TS object. Second step, we run a regression with ITC as the response variable and Nifty as the predictor. We again use the coData property to run this regression. We do a bar plot of with index on the x-axis and the squared residuals on the y-axis. So this was it as far as usage of TSX is concerned. I hope you have been able to understand and you do find value in using this package. Now, as far as the development roadmap is concerned, as I mentioned, this is a fairly new package and a lot of things need to be developed. Some basic functionality exists, but for example, there are certain important things which still need to be worked upon. The first things is to implement tables.jl interfaces for better interoperability. Then we want to do feature parity with Zoo and XGS from R. Integration with impute.jl. We are right now converting the TS object into data frame, then running impute, and then converting it back into TS, which is quite inefficient. We want to introduce metadata support. Again, we will be using the metadata support, which is in works with in the data frames package. Then we want to support rolling regressions. We want to support custom index types, and not only limited right now as it is right now to only integers and time type. Then we want to improve test coverage to make the package much more robust. We want to support duplicate index values. Some people on Discourse and on GitHub have commented on other packages that they are looking for this feature. We want to provide better support for missing values. We want to introduce broadcasting operators. Some of the work is already being done on this. Then we are thinking of certain optimizations for regular and irregular time series. Then of course we will be doing bug fixing and performance improvements as we go along. And a big thank you to Julia Lab at MIT for financial support for this project. It wouldn't have been possible without them. Carlos Parada for guiding with Julia Summer of Code and Google Summer of Code. We have some students who are working with us. And these are the contributors who have helped us by writing code, by doing endless discussions on the design and on the package features, and helping with real world problems so that the package is useful. So thank you.
Hello, everyone. Welcome to this conversation on how we will make progress on Julia and statistics. We've got a bunch of remarkable people here on this call. In the metadata of this video, you will see their profiles. And I would like to get started with the substantive conversation. So our first question, what is our assessment of the strengths and weaknesses of Julia as a foundation for doing statistics? Not the state of statistics in Julia, but rather that if we apply in our mind's eye, if we think some time into the future when a lot of things are fixed up, what's the opportunity, what's the potential, how do we see this evolving, that in what ways are we attracted that there is something good and important here which can make our life in statistical programming better? So can I first ask you for that vision of what is it that makes you feel good about doing statistics programming in Julia? Professor Bates, can I please turn to you?
Yeah, I, of course, feel very strongly about avoiding the two language problems. You know, my background, I worked for a long time on mixed effects modeling in R and had to write either in R and C or in R and C++ and RCPP and RCPP eigen and trying to bring in sparse matrices and all of that sort of stuff. So it just became too difficult. You're juggling too many different interfaces, different languages. So when Julia came along and I first heard about it, it was just sort of, wow, they can do that. And I became very enthusiastic right away. So I think that that's the basic value that Julia brings to people doing statistical computing is the same that it brings to a lot of people in technical computing areas, that you can get the performance of the low-level compiled language while working in the high-level dynamically typed language. That's from the developer's point of view. From the user's point of view, it's, oh, this can be done. I switched to assessing variability of parameter estimates in some models just by using a parametric bootstrap. And why? Because I can fit these models over and over again, tens of thousands of times, and do that in a very short period of time. So it's also composability, the package system, the sort of zen of developing a Julia package is much more disciplined. It's expected that you're going to have continuous integration. It's expected that you're going to have test-driven development and so on. So all of those aspects make it attractive for long-term prospects. The difficulty is that you have to convince people that it's worthwhile learning something new. And that's always an impediment. You have to provide some sort of short-term benefit, which sometimes can be just, oh, this package exists there, which is where I think that the interface packages, rcall, pycall, JuliaCon from either of those is useful because it allows people to dabble their feet in the water and learn a little bit about the language. I'm still at the point where when I do some analyses, I fall back on R through rcall for doing the plots. I love what people are doing in Mach-E. I love the work on algebra of graphics. I'm better at using lattice or ggplotting. So when you need to get something done, having a familiar tool is very important too. So I see the long-term benefits as just, it's a very solid language. It's a language that's built on a very good foundation, but it's still being built. So you don't have all of the nice turrets and towers in the language at present. And that's going to appeal to a type of user who's more on the developer end than on the strict, I got to get this report out by 3 o'clock and I don't have time to learn everything that I need to know before then. So let me pass at that point. Somebody else can take over.
No. So yeah, I think I agree with all that. Although one thing that I do want to note that I think makes Julia such a sort of an amazing foundation is just even for people who especially I guess for people who wouldn't have to learn something new because they don't have something old that they already know. So people for instance, I would probably not be a developer or working on statistics or programming at all if it weren't for Julia, because this is actually, it's like I am usually the kind of person who is a lot more interested in statistics or mathematics or applied modeling than I am in actually coding, and I do not know actually a lower level language like C++ or something like that, and then just being able to right away get straight into Julia and immediately be able to write like I'm used to in Python or R or something simple like that, and have it be actually usable for a package that I want to build instead of having to learn a completely new language is honestly, it's amazing. And I think that that's a great advantage of Julia, that we can get people in so quickly and help them get contributing to the package community so easily, when in the Python community or the R community, you would have to spend God knows how long first learning C++.
Sorry,
grew up in the R world. What has been your experience in the transition?
Yeah, I grew up in the R world, and so I just started learning Julia in Jan 2022. So I'm just baby in that sense. I'm 6 months old in terms of Julia world. So what I found astonishing, I mean, speed is definitely because it's a native language. I mean, you're writing, you don't have to worry about the two language problem as Professor Pitts mentioned. So speed is definitely something, but what really surprised me when I started using Turing.jl, like the way I can write the code, like I can the way I teach Bayesian statistics in class, effectively whatever I'm writing on the board in the blackboard, that directly goes into my code and that runs. And that was like, wow. I mean, if I shows this to my students, they will be like, I mean, the way you write mathematics, that can be codified and that can run and give you the results. That is what actually like make me really, really interested about Julia. And I hope that going forward, the package I would like to develop will be have all those features of Turing.jl, because that is something, it's abstract, but it's absolutely beautiful, because the way you write mathematics, you can codify that in is something is just beyond me. So yeah, speed, I mean, maybe 10 years down the lane, there could be another language which will beat Julia. I mean, then there will be maybe in 20 years down the lane, there will be quantum laptop. I mean, there is no end in the speed. I mean, and we know this game. But the thing that really surprises me is that the way you can write, you can code the language. That's really surprised me. And I'm all immersed in Julia for now, last 6 months.
Vijay, tell us your thought process and decisions around this.
Yeah, so first of all, thank you for this. One of the most important things that the two aspects I have two hats. I have an academic hat, and I also develop products that are commercially sold in Julia. So I want to give you both perspectives. I've been teaching R, and I'm not a developer. I've never been trained in any programming language, but I've been teaching R for statistics and everything that is related in pharma for the last almost 12 years, right? And back in 2016 or 17, I came across a problem where I am not making it up. I had to use a mix of Python, Perl, Fortran, and R, which I spent about 8 months working on. And that turned out, when I actually discovered Julia, and I used, I think at that point, JuliaDB, which is still there, I ended up doing that entire project in one language in literally 2 months, right? And that opened up a lot for me, right? So that was more from a research perspective. And then I realized, man, if I could actually make this happen for people like me in the industry, this would be great. And that's how, the whole productization of what I'm doing happened, right? But from an academic perspective, I completely agree with Saresh in the fact that you codify the mathematics that you write and you're able to teach. That's a completely beautiful thing, because then it's simple. What you write is what you see. It's like the editor. What you write is what you get, kind of. What you write is what you see, and that actually made things a lot more simpler. And that goes to the next point of actually what Professor Bates just mentioned, that it's important to teach, and how you teach, to what Carlos also said. Imagine teaching somebody who's already learned R for a long time versus somebody who's coming in new. I think for the newer generation of population, it's so much more easier to teach statistics, if you are in this interface, then if you have to go through a simple kind of interface where you have to write everything else. So there's a little bit of there's a beauty plus brains kind of thing that's going on here, in my opinion.
Pogomil, do you want to jump into this?
Yeah, so I was thinking what to add, and because there were many topics already covered, but I would say that what is important, especially important in terms of statistics, is one thing that BI just mentioned, but also it could be heard earlier that Julia's strengths become apparent when you start to need to do something longer than 30 or 50 lines of script. So once you really need to develop a solution that is really a bigger project, not just a toy example, that you do on your class assignment, then you can see that the way Julia, in a sense, gives you tools, but also forces you to structure your thinking, allows you to be more productive in the long run. And this more productive, of course, part of it is performance, but I would say it's also just developer or statistician in the context of our discussion performance in terms of how much you can pull off in 1 week or 1 month. And I know Python, I know R, I know everything, all those standard programming languages. As many of you also mentioned, every one of us work with different languages. But when I start a new project and I ask myself, which tool should I use to spend least time to get the result, then recently I always choose Julia. So, because I end up, for example, deciding that what Bayes Julia offers, not even speaking about the packages, but what Bayes Julia offers is like a perfect mix of basic functionalities that you need to build algorithms around working with array-like data. And this is something you don't have in Python, you don't have it in R. Of course, they have functionalities that allow you to work with arrays, but this is always feels like kind of add-on to the language. Actually, in Python, it's an add-on. In R, it's inbuilt, but it's not convenient. In Julia, simply the set of choices, even in Bayes Julia that was made, makes it easy to develop new things, or I would say in general, to implement algorithms. But, and the thing is that the biggest benefits of it you see when you need to do something bigger, because at least this is my perspective, that if I need to do just, reading the data and create a correlation matrix, then probably there is not big difference in which language you implement it. But once you start building something larger, especially that has to go to production later, then the benefits of Julia, I think, are quite significant.
One thing I would like to add to Professor Bogerman's what he just said about performance. I totally agree with him. And having worked with R for many years, I mean, I have no formal training in statistics. My background is computer science. So I have I transitioned into R. It was a long learning curve to think about vectors and matrices as the base on which objects on which to perform. And then when again a little learning curve to migrate into Julia, as Sori said, I'm also like a 6-month-old infant in this ecosystem. But what I did notice is in terms of, let's say, performance, is that Julia makes you think about performance of your code inherently. I mean, it's there, it's built like that. So for example, in R, I learned it over the years that there are things which you learn. So the memory, the garbage collection about the memory, copy and write. You're working with data frames, you change one column, another data frame gets created, and how the garbage collection works. So all those things which you learn over the years. But here in Julia, what I saw is that even the Julia documentation mentions it very clearly. Even the generic interfaces are built like that to support in-place modifications of an object, for example. That is something which I just loved about the language, that the standards are in place to have that performance thinking, and of course thinking about the types that's inherently again built within the language.
Yeah, but here, for example, if you mention this is something I, as a maintainer of data frames, I always have a challenge with this. What I mean by this is that we indeed expose, various possibilities, because you can copy data, not copy data, and you have full control of what you can do. But on the other hand, I always think, okay, so for expert, this is very good. But the question is, and maybe you can comment, when you were doing the transition from R, isn't it creating a kind of steep learning curve that user comes and sees, I have so many options, I don't know even if I need them, so why do I need to learn them?
I guess for me it was a little easier because I had faced those problems. And at one point there was one project where I was working and was handling some 100 millions of transactions a day, that kind of data. And then you had to think about these issues. The data wouldn't fit into the computer RAM, and then you have like multiple computers. You offload the computation to different machines, and then your program crashes out of memory, and then you're thinking, okay, what is happening? Why is it happening, right? So, and that experience I felt sort of helped me. But I do think it could be confusing for somebody who's not seen this problem or had not had this problem or think about it. So yeah, I mean, I can think that, okay, why do I need to modify the object in place? Why can't I create copies, right? So that is obviously there.
Can I segue into a next block of discussion? This is about the tension between building a Julia statistics ecosystem that speaks more native Julia, that is rooted in Julia idiom, that is rooted in the modern computer science that is in Julia, versus the objective of easing the transition path for people who are coming from R or coming from Python and are looking for something more familiar. Okay, there will always be that tension. And how should we approach this question? What are the right ways to make those trade-offs? Bogumil, you have often talked about the question of missing data. I feel that in the field of statistics, we've really got to have transparent, standard default handling of missing data all the time by the underlying tools without requiring overhead on the part of the user, because handling missing data in a certain sensible way, as is done in R, should really be in the infrastructure of a statistical programming system. So I can see how it was important for Julia to implement missing data in a certain way. And there are domains where missing data is viewed differently. But for us as statisticians, observations that have missing data is just completely normal and is a part of our bread and butter. So how should we build a world of statistics and language syntax and packages which are good for the Julia statistics world? And then how should we deal with this tension between the old user base of R and Python versus what is cool and elegant and high quality, what we can build for the next generation in Julia, while leaving some of the old users behind sometimes?
Yeah, so if we mention missings, let me just comment on two examples of the tensions that we have here. So for example, by default, Julia collections like vectors do not allow missing values unless you tell Julia that you want to allow them. So what is the reason for this? There are three kinds of reasons. First reason is that as a user, you can explicitly say, I don't want to allow missings. And if someone tries to put a missing into this vector, I want an error. Because I expect this as a contract not to allow missings. And I think it's quite often useful to have this constraint, because then you have a quick fail of your computations. The second aspect is performance. So not allowing missing values in vectors gives you a bit better performance. Not a big difference, but there is a small benefit of not having missing values for your computations. Third thing is that if you have a vector that doesn't allow missing values by default, this vector uses less memory. So in a sense, you have a situation where not allowing missing values uses less memory, is a bit more performant, and sometimes it's wanted. But on the other hand, as you have said, in statistics, because in other fields like engineering, you very often don't even need missing values. So then people say, this is exactly the choice that we want. But in statistics, this is a opposite from the perspective that most often you would have those missing values. And then you can have to constantly think of how to handle them. And the second, so this is kind of low level consideration. And the second aspect is, for example, treating missings in conditions. So what I mean by this, most users, when they say, I want to filter, for example, data frame by some condition, intuitively think that missing value should be dropped when filtering. While in Julia, it will be an error if you encounter missing value, because you will learn that missing is not a Boolean condition. But now you can think, okay, but why do we have it? And the answer is because sometimes actually you want, for example, missing to be treated as true, not as false. So you say, okay, if I have a missing, I do not want it to be dropped by default. So here we have a kind of tension that there is some behavior like dropping missings when you filter some collection, which is 90% of cases correct, but 10% of times is exactly not what you want. So if it happens by default, then you get a wrong result. But on the other hand, and this is what we have in Julia, at least by default, is that you have to be explicit how you want to handle missing values, but this gives an additional mental burden that in your code you have to do an explicit handling of missing, for example, using coalesce. So you say coalesce X, either true and false, and then you are happy with the condition, but you have to be explicit. While normally people would just write a condition and expect that missing would be dropped. So this is a kind of thing that, again, I am very used to using Julia, so it's not a problem for me when I write my code. But I am always thinking, okay, if newcomers don't find it too demanding to constantly have to think of how to handle missing instead of having the default that is most of the time correct. And I'm not sure which is the best way here.
I would contrast the way that Julia handles missing data with the way that R handles missing data. And R was derived from an earlier language called S, and S was specifically designed to be working on data science, statistical sorts of applications. And they made a decision to incorporate missing data at a very low level. So all of the vector types in R have a missing data sentinel. And it's like one of the man values for floating point, and it's the minimum negative value for integers and so forth. But what that means is that every time that you process a vector in R, you have to have the loop in there to check for the missing value sentinel. And, that's just not going to fly in Julia, because Julia is used by people who don't have missing data and who are not willing to allow that kind of performance hit. So yes, R does it in such a way that it's very convenient and low mental overhead for working with missing data, but it comes with a performance penalty. And I think that in my experience, it's not too much to expect people to think more about how they work with missing data if the benefit is performance.
Can I take us back to the more abstract discussion? How should we think about the tension between building things in a Julia native way versus building things that are more accessible and recognizable to people coming in from R and from Python? Ayush, can you describe your experience in building the survey package, the tension between building something that's clean and nice in Julia versus building something that looks more like Thomas Lumley's beautiful survey package in R?
Yeah, so, and Bogomil has also in an issue pointed it out that maybe it's a better idea to do it in a more Julia way. But yeah, I just felt that there's so many resources available by Professor Lumley. The first version was released in 2000, version 1.0 was released in 2003. And since then, there have been so many documents, so many talks, books, and so on the package. And there are examples, there are discussions on R-help and stat store stack exchange. So it's just that the resources are so widely available that I feel that the transition will be very smooth if the syntax is similar. And also from my own perspective of as a developer, it's a bit easier. And so there's a quote by Thomas Lumley that we don't care about speed in the package and we only care about expressivity. So he has really focused on expressivity, and internally he has sacrificed speed. And he has said that there's no need to fix it until someone really starts complaining. And because data is getting bigger and bigger now, so we are complaining now, but simply moving it to Julia has increased the speed by more than 100 times. And actually internally it's different. So for example, I think he's not using group by and combine that effectively. And because it's so well done in data frames, so internally the code is very simple. There's like some group by and some combine, it's a lot faster. If I were to use a direct translation and do a search operation, then it would be a lot slower. So internally, it's not a direct translation. It's written in a Julia way, but it's just that the API is very similar to the R API. It's not exactly the same because I can't do it, but it's very similar, and I've kept it like that so that people can transition.
So I have a point just to piggyback on Ayush's thing, right? So the question here is, what are we trying to achieve in developing the Julia Stats ecosystem? We're not trying to compete against R. We're trying to build a new ecosystem and an ecosystem that is here to stay. It's okay for people to use multiple languages. People will always use multiple languages. I think that's a realization that I've come across when trying to put a product out there that's competing against a 60-year-old elephant that's there. And, I know what Doug Bates is laughing, but he knows exactly what I'm talking about, right? It's been developed in 1965, 70, and the entire pharma community is still using Fortran 77 and Fortran 90, right? So it's okay for people to use other tools. But I think what is really happening is, in my opinion, if I was trying to be in a governance system for this, I wouldn't try to replicate what's out there. But I would instead invest the efforts into increasing the resources, the education around this. I will tell you, still 2009, 2010, if you look at the growth of R, it was okay. It was growing up. It was not crazy. People were still using SAS a lot. It was only after RStudio's platform launched and they had the simple knitter and publish to RPubs came, people started realizing that, hey, you know what? I can write something and hit publish and my article can go online. They don't have to know anything about coding, about HTML, about websites. And now everybody became a hobby statistician. Everybody became a hobby blogger. Everybody became a hobby trainer. And that is what we don't have in Julia yet. I mean, I'm sure there are packages out there, but it has not become that prevalent. And I think our focus should be on developing the best tools, not worry about pulling people from other tools. As long as we have enough good educational material, I would rather go for that than trying to pull people from other, because you can't change people's habits. If I'm used to brushing my teeth after having my breakfast, you can't force me to have my breakfast and then brush my teeth, right? It's just the way it is, right? So I think it's just going to evolve over a period of time.
So one thing I want to add, so you asked why are we developing this? So actually, I mean, the real reason why I first started writing that code was for an internal thing. So we use a very large survey data set, and it is a usual sight in our office to see people start a code and then leave their laptop a little open for like 5-6 hours. So and then I did it once. It was the first time I was using that data set, and I just could not believe that it was taking so long. So it was actually for me and for like our team that we started doing it. And then even though I've made the code so similar to R, they're still not moved from R. So it's actually just me who is using it right now. But that was actually the purpose of making the package.
No, I understand. I was using that as a context to say that I think a focus should be on education and develop the tool in the right way that is more Julia automatic. That's just my way of thinking.
I was attracted by Turing because I feel that they have pushed the global frontier of how to do Bayesian statistics, and it is completely incompatible with every other system, but it is great. It is really remarkable. And I feel, that's the kind of work we should aim to do, because it just takes us to a different level altogether. It lays the foundation for doing better science in the future. So I'm so excited about using Julia as a foundation to do transformative things. And so, when I look at the work done in data frames, when I look at the work done in Turing, I really get inspired that we should push the frontier, and that will often mean breaking familiar APIs.
So one of the other reasons why we copy stuff, I'm primarily about since we are discussing, the tension between bringing in users from existing languages in R and Python. It's also the ease of use. For me, of course, my opinion is definitely biased because I've worked with R for quite many years. But there are many things which I just, as a user, find them easier. The interfaces are just easier than what I see with some packages, with certain operations, than they are in Julia. So while building a new package, expressivity, as Ayush mentioned, the ease of use also becomes an important point. That it should be, the interfaces should be more, how do I put it, intuitive, more natural. You just feel natural. Okay, if I write this expression, I expect that this is, this should be the default, or, there should be the argument name. All right. So that is another reason for that sort of tension, even though you want to do it in the Julia way, not, provide it as a mandatory argument, but then, with R, you can, everything is a keyword argument, right? So just a little example. So you think hard about which should be the keyword argument, which should be the mandatory, and set some certain, sensible defaults.
So I think that's a very important thing, because now transitioning from R to Julia for the survey, because everything in R is like a keyword argument. So that was really difficult. But at the same time, it's kind of nice in R that you can tell what parameter it is, right? Like if you have f of like 10 parameters, then you can like tell like if x equal to 1, y equal to 1. So I think that's quite nice in R, which is not there in Julia. And it was really painful for me in survey to do it, because then I couldn't do multiple dispatch with keyword arguments. So yeah.
Can I go on to a next question? Bogomil, you have often emphasized that we've got some work to do on the foundations. How do we improve the convenience of using Julia stats? How do you think of Bayes Julia? How do you think of statistics and stats Bayes? That, you know, how do we reduce the entropy in these foundations, and what's our way to fix some of these elementary things?
Yes, so at least my perspective is that let me first comment what, at least from my perspective, the tension is. So I believe that we need some statistical functionality built into the language, because when people want to calculate, I don't know, mean, they don't want to have to install a package, because it seems to be an overkill for many standard simple functions to have to install something. But on the other hand, very quickly you learn that those functions that are provided by statistics.jl, so the standard module, are limited, and you anyway need to have additional packages. For example, the core of the things is, I think, weights, but because other functionalities that are missing in statistics, like order statistics and this kind of things, this is a separate thing. But then if you decide you need something in standard distribution of Julia, then you very quickly hit another problem, that if something is in standard distribution of Julia, you have a limitation that you cannot develop it too fast, because it will be only released as the Julia is released. And also, if you like to change something, you cannot change it because of the non-breaking policy in Bayes Julia. So this is something that I think is really difficult and challenging. At least my perspective would be to have a more complete package that is designed for support basic statistical functionality. So to merge statistics and stats base somehow into one package, but whether it should go into whether then it should be statistics, a standard library module, or rather this should be taken out as a separate package that has to be installed. I'm not sure. I would go for having a standard module. But as I have said, I understand that this will bring us significant limitations in how fast we can develop it. So this is at least the tensions I feel, but my thinking would be to leave statistics in Bayes to have this standard functionality, but try adding things that we are sure that we want added, so that the feature functionality is more complete from the statistical user's perspective. Why I mentioned this, maybe the issue is that, for example, those weights, this is something you need almost all the time when you do statistics, but for example, there are people in engineering who need to calculate means quantiles, and most of the time they don't need weights in their computations because they have equal weights in all of their data. So this simpler functionality that is currently provided is enough for them. But from the statistical user's perspective, which I understand we discussed today, is, and I am within this bandwagon, I think that we should put more functionality into statistics module, that it's more feature completed. This is my thinking, but maybe especially you who have migrated recently from R, you can comment how you find it. Oh, you are muted.
Do others have comments on this question? Okay, we are towards the end of our panel discussion. I would like to just go to our most important question. What's our way forward? What are the priorities for what needs to be done in building the Julia statistics ecosystem? How should we organize ourselves to be more effective? How should we coordinate between all of us on this call and the 100 other important people who are developing in this world? So what are your thoughts on the way forward? What are our priorities and how should we go about doing it?
For me, I would say we really need a way forward to evangelize and educate folks better. I had to use the word evangelize because it's important to continuously be out there and tell people. Ayush is doing it in its own ways in his office, but nobody is listening to him. But eventually, that shift will happen. I'm in the same space in the pharma community where we're trying to move, and it'll take time. We know it's going to take a few years, but the early adopters are already loving it. It's just a matter of time. So it's about putting out the right education and evangelizing it and standing by it. I think that's more important. And there's no question that we have to make it easy, right? There are always comparisons that will be made to R, but I think in one area of focus should be education.
Carlos, what are your thoughts on the way forward?
Yeah, so I think I agree. Mentioning on sort of bringing up Bogomil's point on having sort of this discrepancy between what should be sort of in statistics and in base Julia versus what should be in stats-based sort of thing. I've been wondering if there's like more we can do to make it clear to new users what are the packages that they are very likely to need, what's the sort of thing that it would be really great definitely to have just a sort of more resources to help welcome people into the community and understand sort of like what they are going to need when they are starting out, so they don't have to figure out like what's the difference between statistics and stats based, why are different things in each one sort of thing. And even just for a lot of other packages, it's, I think, very common in Julia to try to split everything up into as many different packages as possible. And that can be definitely very intimidating for new users. And I think we should be trying to make more efforts to sort of collect more of these packages together and make it easier for users to figure out what it is they're going to be needing.
Professor Bates, what are your thoughts on the way forward? How should we organize ourselves? How should we do community building? How should we coordinate better with each other?
Yeah, there's always that tension there that Carlos mentioned between having the Uber package, which is going to encompass everything, and having a number of small packages. I don't know whether one of the advantages of Julia is that it has the composability aspect to it. And we've seen that with packages that really don't have content, like data API, that are just there to knit together other packages in terms of defining some generics. So it may be possible to think of some kind of statistics toolbox. And I think that would be tied in with trying to teach courses. And fortunately, I'm out of that game now, but I don't know what do we want to think about an introductory course in statistics, what would be needed in Julia, or do we want to think of more advanced specialized courses? I think we're still at the point of advanced specialized courses. But the concept of what the community is becoming much more diverse. We have people who would identify themselves as data scientists who may not be interested in statistics in the sense of distribution and probability and statistics and the typical model fitting, but they're definitely looking at the streams for data and so on. We have people in machine learning, which still is a bit mysterious to me. And you know, how do these communities, they at least should be talking with each other, people in Julia community who are active in these. Do they need to be somehow knitted together? I'm not sure. It seems that there's a lot of tension between coalescing and diffusion, and we're going to have to feel our way through to decide exactly how we can balance those forces.
Sarish, what are your thoughts on the way forward? What should we be doing? What are our priorities? And how should we as a community organize ourselves to get things done more effectively?
Well, I think a couple of things we need to done very quickly. One is, for example, what Bogumil says that missing data handling is a very different story in Julia. So maybe we can put up some training material of how to handling missing data, because in typical R Python, that is, we take it for granted, but in Julia it's not. So I think the aspect which is not so obvious in Julia, more training material, YouTube video would be something we should take on priority basis. Another point, I think, with Professor Betts, he mentioned that maybe some more material on, say, introduction to probability and statistics with Julia, those kind of material needs to put on. So I think more training material, what Vijay says, is more important. And also the aspect of this Unicode aspect of Julia, like, you can use effectively Greek letters in your coding. That is, I think, absolutely beautiful thing of Julia. So I think that could be one of the unique selling point of Julia. And I believe we should stress on those. I think, like, it is like being a statistician, being trained statistician, we always think like, like equations first, and the Greek letters and the equations comes naturally to us. So, and you can codify it so easily. That is one of the very strong point of Julia, and that should be one of the part of our training material. So, and things, I believe, as Vijay mentioned, that things will fall in place. So we are not in rush. So I think that is what, and of course, building up the community, reaching out to each other is and Julia Discourse is a great place to be. We need to introduce our students. I'm pushing my students to be active on the Julia Discourse. So, pushing our students to take part in the Julia Discourse is also another thing that we can encourage our students to be on. So these are the things, I think, small things we have to keep doing.
So I think I totally agree with what Vijay has said, and Professor Bates and Ajay Shah carried forward, is the training and education, because I feel all of us scientists and engineers here, we can sit in our garages and keep working on our little products, but what we do really need is more and more users, really. So we need to get out there. We need to reach those people out there who are using data, whether there's data scientists or statisticians, to use the products which we are building, to use the language and the packages. the more users we have, the more evolution we will see. The packages will become better. So, yeah.
Bogumil, over to you for the last word.
Yeah, so my thinking is that maybe let me comment on the coordination efforts from the perspective that was related to those interface packages. So I think that a lot of things will be easier if we really focus of thinking of those high-level abstractions that we can put into packages. Currently, there is a data API package and stats API package. Those two packages are meant to be interface packages, and I think that really there are a lot of functions that could be put there, and if we standardize their meaning, it would make things much easier, because even such a simple function as predict, I don't know if you stumbled on it or not yet, but predict is not standardized in this way. And then if you use several packages that allow you to do prediction from a model, you have several predict functions imported, and then there is a name clash. So this is maybe not a super, I hope this is not a very complex thing to do, but at the same time, it would make teaching, learning, and using Julia easier, because then you can say, there is a predict function, for example. It's in general meant for prediction. And whatever package you use, there is some common interface agreed how it should be defined. And all the packages that support predict function follow it the same way. And then you have two benefits. One benefit is that you learn it once and reuse the knowledge, but the other is also that such a common and intuitive name can be easily reused across packages. Because currently, if you have a common name, you have to really think strongly whether you want conflict with something else that is out there in the package ecosystem.
So Bogumil, how should we solve the coordination problem where a whole bunch of us need to come together and debate this and come to some of these standards? Because Saurish here has taken a different strategy. He's building the CR Rao package. He's saying to himself, look, I'm not waiting for the entire community to coordinate around, but within the domain of my one new beautiful package, I'm giving you this consistent API to a whole bunch of statistical estimators. And so he's making progress, but he's not solving the larger problem. And I see value in both, that it's good that he's building this package and it is giving you a simple, harmonious, consistent API for a wide variety of statistical models. But we also need to solve your problem, which is that there should be a predict generic. So how should we go about it? How should we have a debate and write a standard? It sounds to me like an RFC problem.
Yeah, so I think, of course, this is not a simple task, but what I would say that, if you move forward with exactly what you have described, then eventually it will become a de facto standard. But the thing is, because this is the crucial thing is here about naming. So if you see a function that actually you believe that the name, because the crucial thing here is a name, because it's related to name clashes. If you feel that you are building or developing a function that actually can be more generic, I would go forward in the package with what you do, but then to submit a proposal to either data API or stats API, depending on what kind of functionality this is, to discuss whether a common API should not be introduced. And let me give you an example of a recent effort that we do exactly in this way. So this is related to metadata. So there are many storage formats like formats like Parquet or Arrow that are currently supported in Julia that allow storing table level and column level metadata. But we do not have any currently. There is a generic metadata package for Julia that allows you to attach metadata to any mutable object, but we do not have standardized on how metadata should be handled for tables. So what we did is the following, kind of what you have described. So we went forward to define an API for metadata in data frames. That is an open PR in data frames, but in parallel, I have opened a PR to data API to standardize what metadata should be on a table level. And why is it important? Because after we are done with this, then there are simple PRs to Arrow.jl and Parquet2.jl that don't have to be data frame specific, but can be generic. And we will immediately have the ability to save and load tables that have metadata, and automatically they, in a data frame, you will have this metadata. So at least what I do, and actually, if someone is interested, this is an ongoing effort right now, that if I add functionality that I believe is more general than just data frames JL specific, I in parallel open appropriate PR or issue depending on how mature the idea is to either stats-based storage, stats API or data API to discuss a more general solution that can be done this way. Actually, there is another example of this, just to give you a brief example of such a situation. And this change was actually prompted by some needs of the users. So there is a commonly used function is in R that is expand grid. And then we discussed, okay, it would be nice, it would be nice to have it in data frames. But then we realized that actually this is not data frame specific functionality. Any table could be expanded like you could define a Cartesian product of input columns. So what we ended up doing is exactly the same. So we added a function to the data API that says, I give you columns, I give you a target table type and materialize it for me. And in data frames, we just have a specific implementation that uses this general API, but you say just, okay, and the target should be data frame, and then data frame is materialized. And of course, the risk is that some users might feel that this is an overkill that we add this data frame, but I think it's not that bad because you are explicit. But at the same time, if someone in the future wants some other table type to support the same, you will have the same function. And on the other hand, I think that this concept that you have many table types in Julia is something that people learn very fast, because when they read their first CSV file and use CSV read, they learn immediately that the second argument they have to pass is the type of the target table that they want to use, because data frame is on one of them. So if you want data frame, you have actually to explicitly say that you do CSV read into a data frame. So at least this is what we do, and those two examples are just of recent kind of this approach. So what I would suggest is that go forward with your functionality as fast as you can, because we need new functionality. But if you feel that there is some part of it that is more general, just open an issue or PR to the API package to make it generic.
Okay.
Just one question to everybody here. So specifically to Professor Bogomil. So you mentioned stats API, you mentioned data API. and I know about tables.jl and how beautiful it is, and it has eased the conversion from one table type to another. But are there any other such packages which are defining these interfaces? And as package developers, we need to be, from what I understand, is we need to be aware of each of them just to just to know where to even raise a PR and such a thing exists, right?
Yeah, but that's why there are not many that packages. Actually, there are only two interface packages, at least in our ecosystem, which is this data API and stats API, because tables.jl is not an API package, because tables.jl defines an interface, but also provides implementation. The point of data API and stats API is that there is no or almost no implementation. It's just a definition of API. It's like, abstract function. I would say that. I don't say how it works. I just say what it does, and everyone who wants to support it can reuse this name. So then there are no name clashes between packages. So in general, and of course, then there is a tension, does everyone follows this? But I think that if I am maintainer of some package and I learn that interface package defines some common function, then I'm likely to follow and just extend this generic definition. Maybe one small comment is for the people who listen to this, why do we want packages that only define interfaces without implementation? The reason is that this approach ensures that those packages have very low dependency, like burden. So they do not introduce many dependencies on yet another packages. Plus, if you depend on such a package, you do not add a lot of compilation time to your package, because those are super lightweight packages. So there is no risk that someone will say, I don't want to depend on this interface package because it's too heavy for me. They are on purpose very lightweight, so that you don't have to think whether I want to depend on them or not.
Okay. Thanks a lot, Bogomil. Sarish, you should build it into the de facto standard, and then we should come back and think about how it can be generalized much more. So, are there any other thoughts and comments? For the rest, I will bring this conversation to a close. I thank all of you for having been here with us, and look forward to engaging with everybody who watches this video through the future of the Julia Statistics ecosystem. Thank you.